Okay, welcome back to Gökova Online seminar series. And this is the second of this series. It is conducted wonderfully by the team of Joe Brandel and Felix Schlenk. And then today, there will be the fourth and the final lecture of this series. And this has been a great series. I learned a lot. So thanks again for this pair. I think you guys might be starting a new trend now, the 2+2 series.
Yeah, it's a bit easier than the one.
Yeah, I think it's fun. Yeah, it's fun. So take it away. Take it away, Felix. We are all ears now. Yeah,
thank you very much, Simon, and thanks for everybody joining again. So today I briefly wish to complete the proof of the staircase. Of course, you remember this is the embedding problem. You have a four-dimensional ellipsoid, and now if picture is like this, and you wish to embed it into a ball as small as possible. And these functions are kind of, people like them because they connect symplectic geometry to other fields by numbers. And here is a typical example. These numbers showed up, and then similar numbers were observed in Viana's tori. And then it took 8 years till finally somebody saw the connection. I should have seen it anyway. So if one really goes for it, one probably sees it. We thought it's a coincidence. So briefly, I want to finish why these steps are the answer. So we already sketched, and maybe you repeated that it is enough to prove that at these special numbers an, a sequence A1, A2, this is A1, A2, they are all square numbers. We have full volume filling embeddings of the ellipsoid 1an into the four-ball of capacity root an, right? We must show this up to some little epsilon, and then it's arbitrary. You always take the supremum. So we have to find these volume filling embeddings, and the first proof was very cumbersome, just showing even by computer programs that there are no obstructions from J-holomorphic spheres. But now, thanks to the almost toric vibrations, we can do that easily in a much faster way. The point is, for every such an, we will simply find almost toric base triangle that accommodates the right triangle. Okay, and let me show this. So who is the triangle and who is the ellipsoid we want to see? This was old stuff, and now it comes. So I first do the second one, the A2. We already proved that this here is an almost toric base. And this triangle here, you only have to look at the integral weights at the boundary. They are 1, 1, 4. And this triangle is SL2Z equivalent to this one that I like a bit better, 1, 1, 4. And here you see this is the moment map of an ellipsoid of side lengths 2 and 1/2. So we scaled a bit differently because in this business, I first assumed that CP2 has length is 1, 1, 1. And herein, since we are free to take these pinching lines, these pinch tori here as close as we like to the boundary, we can up to an epsilon indeed just put an ellipsoid into this almost toric vibration, but this is CP2, so this ellipsoid is there. So of course I do not fully claim that this is an explicit embedding, because we came to it by this shear, but on a set of volume percentage as large as you like 99.9%, the embedding is actually explicit. Okay, so we get this embedding, and so now actually we wanted to embed into the ball. So you have to make sure that this ellipsoid does not touch, is disjoint from the line at infinity. But this is general knowledge. This was known in 92. That an ellipsoid embedding or an embedding of a disjoint union of poles can always be arranged such as to avoid a complex hypersurface. It's actually true in all dimensions. So I don't go into the proof. This comes from the knowledge 30 years ago. So we can really avoid here the CP1 at infinity, and therefore we get an embedding here because of course CP2 without the line is just a ball. And now you scale everything by a factor of 2 and get exactly the embedding you wish to have. Right? The 1,4 embedding into the 2 ball into the 4 ball of essentially the same volume. And the epsilon can be killed. If you take here closed domains and open targets, you can even go to the limit. But this again needs kind of machinery, well-known machinery. And the general picture is exactly the same. So we go into our Markov tree of Vienna, and we observe that the good branch is the upper one. Exactly the upper one, because only there are ones. Exactly there we have a 1. And if we want to embed an ellipsoid, we want to have a good corner, a standard corner, which has a 1, and the other angles are maybe not 1. And once you have moved up the 1 in the Markov tree, the sum goes up. So you cannot come back. So just from Markov theorem that these are all solutions, we know that for us, useful is only exactly the upper branch and these two, right? So what I now must show, we checked it for this guy, we already checked it for the 112, which corresponds to 114, one always takes squares. We have to check that these Markov numbers are exactly the Gn plus 1, the Fibonacci numbers encoding our ellipsoid, right? Okay, let's do that. So I claim this, that the odd index Fibonacci numbers here are exactly the Markov numbers. And this simply comes from the Markov equation and the recurrence relation defining the Fibonacci numbers. Let's check it. Sometimes it's nice to have these things in numbers. So the Markov equation collapses a little bit because C, one of them is 1. So this is our equation, and I claim the solution of this here are exactly the pairs Gn plus 1. And then everything is proven about this Fibonacci staircase thing, right? Okay, let's do it. So I look at the upper branch because I know the upper branch, in the Markov tree, these are exactly the Markov triples containing 1, 1. Okay. So I always order them, an is less than bn. And of course, by the way it's done, the next one, the an plus 1, is the old bn. And the new thing is 3bn minus an by the Markov move. This defines these Markov numbers. And by induction, we assume that what we want is true. Because at 1, 1, 1, of course, everything is true. Okay, now you compute the new guy. You insert the an plus 1 is the bn. The bn plus 1 is given by the Markov move. The bn is indeed gn plus 1 by induction, right here by induction. Then this I also rewrite, bn and an are inserted. And now I use this equation that you immediately prove just using, fn plus 1 is f, or fn plus 2 is fn plus 1 plus fn. And if you now apply twice, because the gn are f2n minus 1, you immediately prove by induction and using this relation that this is true. And that's it. So here is nothing going on. Once you observe it, you cannot not prove it. Okay. I think the only interesting thing is that these things really are related. The Markov numbers encoding the almost tori vibrations of CP2 over a triangle, well, starting in this way from the usual CP2, are exactly related to maximal embeddings for the embedding problem ellipsoid into ball below tau to the 4. Great. Okay, fine. Good. Now I wish to, well, the whole talk is, the main goal is to say that almost toric vibrations are useful. And I will now give 2 more applications, namely construct infinitely many exotic Lagrangian tori. Exotic, as Shoei already said, means that they are not standard and not symplectically isotopic or Hamiltonian isotopic to anything standard. And then if I have time, I will also speak about cube embeddings. Okay, so first, Viana's theorem that was probably earlier detected by Galkin and Usnich and Galkin-Michalkin, but they wrote very slow. Or maybe Viana wrote very fastly. Okay, so the statement is that there are infinitely many Lagrangian monotone, otherwise it's not so interesting, monotone Lagrangian tori, that they are different in a certain way. In standard spaces like CP2 and the 4-ball, by now we have many, many more. But I focus on this first result.
Could you remind us monotone, what monotone meant?
Yeah, monotone, yeah, okay. So monotone means symmetric. And this is not quite a definition. So if it were the two-sphere symplectic manifold, then it would mean that the circle divides into equal areas. If it were an n-torus, that is a product A1 dada AN in Cn, it would mean that all AI are the same. If it is a fiber torus in CP2, it's only the barycenter and nobody else. And the technical definition is that the area homomorphism, on pi2, on relative pi, you have a symplectic manifold and the Lagrangian therein. And now there are two homomorphisms, one to the reals. You evaluate, so you take on the Lagrangian a disk representing this and integrate it over omega, the area homomorphism. And then you have another homomorphism going to the integers. It's for every such disk you take, it's the Maslov class. It's a Maslov index. It's a Maslov. The second one is the Maslov, and the first one is the area class. Okay, and these two.
Maslov is something to do with C1, right? Maslov is something to do with
Maslov
C1.
is, if it were, spheres are also disks. If the disk happens to be a sphere, Maslov is half of C1.
I see.
Is proportional, and you want that the two are proportional. I guess positively proportional, but I've forgotten. Mine are always positively proportional, and we normalize the symplectic form such that the proportionality is 1. That's the best normalization. This means monotone. So monotone is somehow far the most interesting thing. They are rigid. They have intersection properties. Their Floer homology is immediately well defined. If not, things are either not interesting or much harder. But sometimes they are interesting and they are harder and they are still solvable thanks to modern theories of Fukaya or Onaoto. But this goes much further. But classically,
do they behave like algebraic curves, like when they intersect, they have to intersect geometric intersection, same as algebraic intersection, because you are saying that they are rigid. Do they have properties like that?
No, they are rigid in the sense that, this exactly, I don't know, but so you see, let's look at this example. The equator that is monotone cannot be moved away from itself by a symplectic isotopy, because you always have to bound half of the area. So any image must intersect, right?
Okay, yeah.
But if I take a circle that has here area 1 minus epsilon, here 1 plus epsilon, I can turn around this axis and move it here in a Hamiltonian way. So intersection rigidity is one phenomenon, but there are other rigidities like Maslov class rigidity that it can be at most, it must be at least a certain. So the general thing is, if you don't want to go into either empty statements or technical real hard technical complications, you should speak about monotone ones. And many are monotone. Many natural ones in physics are monotone. Usually if in physics something appears natural and interesting, it's monotone. Of course, inside of the Lagrangian manifolds, the monotones one are a zero measure, but they are the good ones. Fine. Okay. And now we will construct infinitely many monotone ones in a ball or in CP2. And the statement is that there is no ambient symplectomorphism mapping one to another of these different ones. But let's say Hamiltonian isotopic. The difference is not big. Okay. So here, so these infinitely many ones, you can give them names because they directly come from the almost toric vibrations, really directly. Because for every Markov triple, right, we have this almost toric vibration over the Markov triangle. This is the 1, 1, 1, and this is the 1, 4, 1, and so on. And in the middle, so what does it mean middle? Here it's a barycenter, and here it's still the same point. You know, we did like this, tuck, and then this we sheared down. So I mean exactly the same point. Here is a certain torus. And I claim that this Lagrangian torus is different, is not symplectomorphic to the Clifford. This guy is called the Clifford torus. It's the monotone Lagrangian torus everybody would write down in CP2. It's as canonical as the torus of size 1, 1 in C2. And this one is not symplectically the same as this new torus. This is in fact the Chekhanov torus, but then we have infinitely many. So more precisely, if these tori were the same, the triples must be the same. The Markov triples are complete symplectic invariants of these tori, right? And these tori are kind of explicit once you find that this vibration is in a way explicit. We only sheared a bit around. It's not so dramatic. Mm-hmm. Well, it's actually true that near these slides, something not so clear happens. So maybe they're not that explicit. So let me prove this. In a way, I think we know. Because, okay. No, we don't know. So now everybody besides Joey Brendel, Juha Chekhanov, and me would say we have to use J-disks. And since we must use J-disks that we can count, we must use, and that are kind of invariant, we must use Maslov index 2 J-disks. These are precious objects. They are J-holomorphic maps from a disk to the symplectic manifold M omega, endowed with a, in a way, good, almost complex structure with boundary on the.
What are you calling J-disks?
Yeah, J-disk. J-holomorphic disk.
J-holomorphic disk.
J-holomorphic disk. We call them J-disks.
Okay, thank you. Okay,
if J is specified, J-holomorphic, if not, maybe pseudo-holomorphic. And these are great objects, but they are hard to kind of understand and to count. Sometimes, so what Viana did, he showed that along the tree, the number of those goes to infinity. So infinitely many of them are different. But if I'm not mistaken, he did not show that all of them are different because the precise enumeration of these J-disks is difficult. But now I present a much easier way. I do not say that this is just killing their work, because these J-disks are very important things for other reasons, like computing fluoromology, computing intersection patterns. But in order to distinguish these Lagrangian tori's we want to distinguish, you can do something much easier. And this is what Joey already alluded to. You need a symplectic invariant and you need Chekhanov's idea. Chekhanov used a different invariant, not displacement energy. He used the first Eklund-Hofer capacity. It doesn't matter. In CM, that was enough, but now we need, this is a good invariant. So I will use this invariant, and then I will look at nearby tori, and the behavior of this invariant at nearby tori will distinguish the central tori. So what we will do is we will take this Clifford torus, for instance, and we take the first Viana torus, let's call it Chekhanov torus, and then we assume that the two are symplectically related, but then it would mean that nearby tori are mapped to nearby tori, right? And then on these nearby tori, we compute this symplectic invariant, And since it's a symplectic invariant, the behavior of this function at nearby tori should be the same. And we will show it is not. It behaves different as a function. And as Shoei already said, we will not compute, you see the space of nearby Lagrangian tori is infinite dimension. It's like a function space, closed one forms. But it's enough to do that mod hum. And thanks to Einstein, mod hum looks like near zero at the first cohomology. So here it will just be a little disk in R2, and these functions will behave differently on these disks, and therefore these tori must be different. That's Chekhanov's idea, versal deformations. So the invariant, I briefly repeat. So Hofer's idea was to do some cost function business. You have a set A in your symplectic manifold, and you want to displace it from itself by a Hamiltonian diffeomorphism. It's a transport problem, and you want to do that as cheaply as possible. So sometimes you cannot disjoin, but if you can disjoin, there are always infinitely many Hamiltonians that do the job, right? You could, for instance, once you have displaced, compose with a Hamiltonian having support here. But there are really many, many choices. You want to do it as cheap as possible, and you need a cost function on the space of Hamiltonians. And the cost function is very strange. In hydrodynamics, it would be the C1 norm. You would take the C0 norm of the vector field. But in symplectic, Hofer's deep insight was that you should take the C0 norm. Imagine the Hamiltonian does not depend on time. Then you could forget this integral and just take the oscillation, the max minus the min. But if it depends on time, you integrate that over time. It's essentially C0 norm. You can always arrange the Hamiltonian at every time to have minimum equal to 0. So it's just kind of the height, the integrated oscillation. Okay? And then you do that for all Hamiltonian that do disjoin and take the smallest cost function value. This is called Hofer norm, and that is called the Hofer energy. Okay, and this number we will compute for nearby tori, thanks to the almost toric vibrations. Okay, that was repetition. And now I very briefly repeat Chekhanov's idea. Why does it not? Okay. Okay, and now actually come very important exercises. You could never really go, but so I give them to you, and at the end, if you have time, we will not, I will do them for you. So I invite you to prove this inequality. So you take a disk of area something like 1, and you should prove, of course, it's in C, it's in the plane. And you should displace it. Of course, one can displace it. One can always, you know, the Hamiltonian function, h of x, y equals y, maybe minus y, has Hamiltonian vector field ddx. Of course, it moves to the right. So it will be finite. But I invite you to show that you can do it with area, with Hofer oscillation. You can find a Hamiltonian function that has minimum 0 and is everywhere less than a plus epsilon for a given epsilon. And I give you a little hint. You should take the disk, take a symplectomorphism defined on a much bigger disk, map it to a rectangle like this. And here is like, this is maybe 1, and this is A. And then you very easily can find a Hamiltonian that will have, you know, ddy as Hamiltonian vector field that moves it up. You use it, essentially you do an interval across something like this. So it's up to smoothing, it's linear. And then it moves it up. And if you compute a little bit, you see that you need exactly oscillation A plus a bit more because you smoothen. Okay? But it's kind of an important exercise. For it, this little trick.
I missed something. You first found this rectangle disjoint.
Yes, I first mapped the disk. No, I first mapped the disk to a rectangle.
But then you say yeah, go ahead.
And then I argue that the displacement energy is, you know, it's in a symplectic invariant. When I do it for a symplectic image, I also did it for the disk. And the exercise is easy on a rectangle and hard on a disk, directly. It's much better to do the exercise not for a disk, but for a rectangle.
But when you move it up, it intersects itself. You don't want that. You said you
No, I must move it up completely. Only at the time 1, it will be disjoint. Time 1 maps.
I see, okay.
You move, for time 1, you have to choose the slope of the no, you define a certain function f of x and y. It will be a function depending only on x, and it will look something like slope a from 0 to 1 plus smoothening, and therefore a plus epsilon. Such a function will do the job. But okay, it's an exercise. It's an important exercise because the other inequality is not easy. It's elementary, but there is no easy proof. There are about 3 proofs, but no easy proof. So the equality, the bigger or equal, is pretty hard. And it was already proved by Hofer long ago. And this was a really important step. Such theorems also are true for balls in all dimensions and polydisks. And he used the calculus of variation, critical point theory for the action function of classical mechanics. So here really a relation between symplectic topology, geometry, quantitative measurements, and Hamiltonian dynamics was established. That's why it was so important. It linked things. So Gromov linked symplectic geometry to J-curves, and Hofer linked it to Hamiltonian dynamics. And this was really conceptually very important. There is a theorem by Chekhanov that gives you a one-line proof. He proved that if the set happens to be Lagrangian, then when you look at holomorphic disks that are non-constant and have boundary on the Lagrangian, then the minimal area of such a non-constant disk will always be a lower bound for the displacement energy. So this is very general and very useful because when you have a circle in the plane, a non-constant holomorphic disk by something like a complex analysis 1, must look like this, or go around several times. Then the area is A, and then you have the lower bound you want. But this theorem is pretty difficult. This is not elementary. This is almost Floer theory, but this you can learn in the book by Hofer and Zehnder. Is a textbook for students. This is very elementary. You only need a little bit of Le-Rechauder theory. That's it. And Fourier analysis on CN. Very good. So we know that the displacement energy of a disk is its area. This is an important starting point to know. And this idea, Joey already said, we look at our Lagrangian, then we look in the space of all Lagrangians, let's say of the same different type, that's enough, at the neighbors. And Weinstein tells us that if locally we mod out the Hamiltonian action on ambient space, we see exactly locally the first cohomology. You see, it's easy to, it's actually, let's take as a symplectic manifold a cylinder. And now let's take a graph here, a graph Lagrangian. And such two guys are the same if and only if the area of the annulus between the zero section and him are the same. Yeah, but this is exactly, I mean, they are sectioned by a closed one form and they are cohomological representatives. And they are, of course, cohomologous if and only if the period is the same. And this statement here is just a generalization of this picture on an annulus, on a cylinder, nothing more. Okay? Now, since our energy function defined on the space of all Lagrangian is invariant under Hamiltonian compositions, as we all actually on the symplectic, we see that we get a function on this quotient. So we get a function on the first cohomology. What it means is we have our Lagrangian and we take a nearby torus, And if we would take another nearby torus that is in the Weinstein neighborhood homologous, we get the same value. So we actually get a function on this finite dimensional vector space with values in 0, infinity. It could be that somebody is not displaceable. It's usually true for L itself. You see, if the value for L were, if you have two monotone ones, then even if it's displaceable in Cn, it's the same. But what happens in CPn or in CP2, the value at the monotone is infinite. He is not displaceable. And this is also true for all Vienna tori. So infinity and infinity do not distinguish anything, but the neighbors are essentially all displaceable, and their values behave in a different way, and therefore these L's we want to distinguish will be distinguished. I already said, but I like the idea so much, I will repeat it again. Are there questions?
So the function itself doesn't tell if they are displaceable, but we have to move it a little bit.
Yeah, we have to look at neighbors. We have to look at neighbors, versal deformations. The neighbors, the behavior of the neighbors of L is a great invariant of L. I think this probably comes from algebraic geometry. It's called versal deformations, but I have seen it only here. Okay, so now we must compute this function. So it will actually be very short. It's very strange how easy it is. So we will compute now completely this function on CP2, and then, because almost toric vibrations are so easily related by mutations to the mother vibration, the real toric vibration, we will immediately find the function EL also for the other tori. But first we must do it for the toric vibration, the standard toric vibration of CP2. So here you see the moment polytope, and I claim the following. If I take a point over him, I have a torus, and the displacement energy of this torus is simply the distance to the boundary. But the integral distance, the affine distance. So here it's this, and here it's the same, and here it's the same because it's not this, it's this, it's the integral distance. For the integral distance here, you have to go either vertical or horizontal. You have to take, okay, the integral distance along a vector, it's not important, okay? So these triangles are all level sets of the function E Clifford B search. There is a helicopter action here, sorry. I live near a hospital. So the level sets encode actually the polytope, and this will be crucial because it will mean that once we have different polytopes, we have different functions E because the level sets are given by the boundary of the polytope, and therefore if the bases are not SL2Z related, then the tori are different because everything will depend on a choice of basis of H1, and therefore it's only up to SL2Z, but that will be enough for us. Okay, so now I compute this picture. There are two ways, but I used the easiest way in the world, which was found by Jouet. So we will prove less or equal by symplectic reduction and bigger or equal by symplectic reduction. It's very efficient. I will always catch it, but I think you get the picture. So I have to show that the displacement energy is less than the distance to the boundary. So I take this point X to fix the idea. I take it here and not somewhere here. But actually, I do briefly something. You see, this is totally the same as this, and it's totally the same as this, because of symmetry of CP2. So you can really choose your point, if you like, just somewhere here or here. There is no cheating. It's when you repeat, you maybe think I cheated, but I don't. Okay, very good. The distance to the boundary of this point here is this, right? And I must show that I can find a Hamiltonian function such that given epsilon positive, its oscillation is less than epsilon, and this torus here is this joint, is made this joint under the flow of H from itself. Okay, so this distance here is my number D. And now we choose a segment in the same direction, but longer. And since this, you see, for this example, I choose a segment so that it is longer than twice D. I could go even closer, but this is enough. I choose such a segment that is longer than twice this distance. Now, you do a certain symplectic reduction that I will not write down, but geometrically it means that. So what do we have over this segment? Yeah, over this point we have a T2, and over this point we have an S1. Now, in a way, I kill one S1. So what happens is I will then have circle, 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 circle point, which is a disk. And the area of this disk is more than 2D. Because the way it's done, symplectic reduction, is exactly that is the length of this segment. I don't go into detail, but it's easy to believe. So I also do it, this disk, I also choose such that inside I have here, you see, this Tx is of the form AB, and A is this and B is this. So A is actually D. I also take this disk, well, by the symplectic reduction construction, this will happen, such that I have here a disk of size D, whose boundary is exactly the smaller generator of my product torus. You best believe this. It's easy to believe, and Schoe has also written it up. But it would take a bit too much notation to make it in detail. I just work over the preimage of this segment, and there I take a disk. And now in this disk, I will do completely trivial two-dimensional things. I now choose, this is the big disk that includes area more than 2D. And in this disk, I have this small disk, the circle enclosing area D. And now I take a Hamiltonian isotopy with compact support in the big disk that moves the red disk to the complement. It looks ugly, but if you did the exercise, you will first move the big disk to a square, to a rectangle, and then simply move this to this, duck, by a linear move, and cut off the Hamiltonian. Again, you do the disconjugacy. Writing down explicitly a Hamiltonian isotopy doing this job is difficult.
Here, red disk and blue disks have the same area?
Yes, yes.
I see.
Blue is image of red, and I was maybe not very careful. But this assumption was key. Otherwise, I cannot do it. So good. Now we have this Hamiltonian H, and now you can lift it to the total space. When you do symplectic reduction and have a Hamiltonian in the base, you can always lift it to the full space in such a way that nobody exceeds. So H was maybe between 0 and the max of H, right? A certain maximal value. And the H tilde also has image exactly this interval. This is an easy construction. So since I could do it for H by Hofer norm less than D plus epsilon, well, it's actually the same, also for H tilde. And this proves, and now, since the flow downstairs disjoint this circle, of course, the lifted flow will disjoin the torus I want to disjoin. In the picture, what happens is something like this. Now I must go back. The torus was here. And in a way, we moved him out along this segment. You see, a torus is a circle cross circle. We moved a smaller circle, but if in a product space you disjoin one factor, you disjoin total space. That's it. Right? Okay, so this is one inequality. And the other inequality is the other way around and also does symplectic reduction, but it sees CP2 as the reduced space, and the bigger space is C3. This is the picture in the Dale-Sound construction. So in the Dale-Sound construction, you reduce along, let's say, the 5 sphere here of radius 1. If here the area is pi, yeah, you have to rescale radius 1 over root pi, which sits in C3, and here you do symplectic reduction. Now, what Schoe explained, either he said, or you could almost get from what he said, is that if downstairs in CP2 we have such a torus TAB, here is A and here is B, then under the projection, the preimage is exactly the torus AB, and then the remaining affine distance. 1, here is 1, minus A minus B. This is how it comes. Not very hard. All written up nicely by Schoe. Good. So now, if the Hamiltonian isotopy H downstairs in CP2 disjoins this torus, I do exactly the same thing as before, and I can disjoin the torus upstairs, which proves that upstairs again, the energy we need is less. But this product torus in C3 is sufficiently well understood. So it's not done by Hofer. Hofer did it only for a circle in the plane. But adapting the machinery, again, by the calculus of variations, you could also use Chekhov. You find that the displacement energy is the minimal entry here, the minimum of A and B and 1 minus A minus B, and it's the distance to the boundary here. You could use, again, the calculus of variations, or you could again use Chekhanov's theorem about J-disk for the standard J structure in C3. No, I did not say everything, but I wanted to tell you which parts enter, which part of arguments. Essentially, when you are very fit in symplectic reduction, you get this all. Fine. So this establishes this picture, that the displacement energy of a torus for the red point in the center, it's infinite, and for everybody else, it's the distance to the boundary. Okay, so it's actually not even a germ, it's globally. It's everywhere except at the boundary where we do not have tori anyway, and not in the center. But it would be enough to have it for an open dense set around the center. It would be enough to distinguish functions. So now I wish to use this computation to compute the displacement energy on other tori, on the Vienna tori. So what happens? You see, what did we do here with Vienna mutation? Yeah, we took half and sheared it down. But this shear is in SL2Z, this operation. And, okay, wait. Okay, well, you see, in a way, this was only coordinate change. Of course, you see, this torus here is really this torus. So its displacement energy doesn't change. This torus here is now this torus. But since this move here is by SL2Z, of course, the displacement energy is again the affine distance to the boundary, because SL2Z maps do not change affine distances, right? So it's a bit short, but what it means is that in the new picture, in the new almost toric vibration, the displacement energy function of this new torus, hopefully new torus, the first new guy, is again simply given by scales of the boundary curve, of the boundary triangles, because it's the affine distance to the boundary. So the outcome is when you go just slowly through what displacement energy is, and you find that for all these tori we constructed, whenever you have this almost toric vibration, you have here this hopefully new torus. What is the displacement energy function of this nth torus? It's the level sets are just given by scales of the boundary. Now, by the symplectic invariant of displacement energy, if two Lagrangian tori would be symplectically related, then there should be an SL2Z map such that the precomposition of one of them is the other one. But this translates that the associated triangle, since the energy sees the shape of the triangle, it means that the two triangles should be SL2Z related. But the integral angles are, of course, SL2Z invariants. They are determinants. So it would mean that the set of integral angles should be the same. But they are the Markov triples, and they are all different. Okay? Now it's a little bit fast.
A dumb question. This shearing is a SL2Z map, right?
Yeah, because it's a transposed inverse of the monodromy we computed.
I see. So when the shear, and then I see, then combinatorics part comes from there, the Markov things.
Right. They are in the Markov trees, everybody is different.
I see. Thank you.
Actually, I think it's an open question whether all the Markov triples are different. but they are in, so the statement should not be for every node in the Markov triple we get a different torus. The statement should be, no, sure. I think it's known that the triples must be different, but it's unknown whether one number can repeat. I always forget. There is a famous conjecture about the Markov tree, right?
No, but it's known that you get for
the triples are always different, right?
Yeah, sure.
Yeah.
Conjecture says something different. Conjecture says the biggest of the three numbers determines the other.
Right. Thank you. Of course, ones appear in several ones. Thank you. Good. So this completes the easy proof of the existence of infinitely many different monotone Lagrangian tori in B4 and in CB2. And it was, of course, done by Vianna using J-disks, but we gave here a different proof using displacement energy. Fine. So now I prepare something in case I'm too fast. I'm 11 minutes too fast. So I brief what you like to do. Either we do an exercise or I give you a third application.
You choose.
Okay, let's do the third application. I want to study an isotopy problem. You see, famous theorem by Gromov says the following: you take R4, right? You cannot see. Can you see my writing? Okay, yes. Because I see you.
Yes.
And then you take out an R. Everything is R4. You take out an R3, and then you glue back here. You glue back a 3-ball. So it's like a room, 2 rooms with a connect. There is a wall, but the wall has a hole. Okay. So this here is an R3, but then you glue back in here a ball, let's say of size 1, a 3-ball of size 1. And now you take here a 4-ball of size A bigger than 1, and here another one. And you ask whether you can symplectically move this ball to this ball in the camel space. Camel space means there is this, well, what I said, this you take away from R4, right? Whether you can move through. So you should make, in a way, you should squeeze a bit. And Gromov says it's impossible. This is called Gromov's camel theorem. It's different from his non-squeezing theorem. It's about isotopies. So, of course, in differential topology, any 2 balls in a connected manifold are isotopic smoothly. And in volume geometry also. always, can always adapt. But in symplectic geometry, you cannot isotope around as you like always. And this question was a kind of not much developed, and it turned out that these almost toric vibrations can say a lot if the domain is something else than a ball. So you see, we look at, okay, you take generally a good set in some R4, R2n, you take a connected domain, and then if you can embed, you want to know how much, the biggest ball, the biggest cube you can embed, this is like non-squeezing. If you can, you wish to understand whether the space of such embeddings is connected or not. And then if you have solved that, you can even maybe compute the topology of that space. So here we have 100 papers, I mean, our community, here about 8 and here about 3. So these topics are almost untouched. And with these almost toric vibrations, one can say something about question 2. And I will now do that. So this is the picture, right? You have target space and you have some domain and you have 2 embeddings, and you would like to know whether you can ask different questions, whether you can find a Hamiltonian isotopy moving the red to the blue, or whether you can find an ambient symplectomorphism mapping this to this as a set or such that you pre-compose the map. You have to say what you mean, but this thing actually will give the strongest. I will not insist in this. So this I already discussed. And as a counter thing, I should mention that McDuff proved that if you take a 4 ball and you take a bigger ball, then the space of symplectic embeddings is connected. This is what was kind of important breakthrough in this business. So here, sometimes the pi 0 is just, well, 1, trivial, or maybe sad, I don't know. Anyway, connected, right? If not empty. And there are generalizations of this. But we will now show with these almost toric vibrations rather easily that if you take as a domain a cube, so you take something like a cube, but for me a cube is a disk cross a disk. It's a little difference. And you map into something like a ball or a cube or a CP2 or something. Let's take a ball. Then if the sizes are well chosen, you can find infinitely many different embeddings in the sense of isotopy. So they're not just the second one. Like in Gromov, for instance, it's totally unknown how many there are. So there is this and there is this. So the number of components is at least 2. It's unknown whether it's finite. It's unknown whether it's 2 or 3 or infinite or something. The problem is that the embedding could be absolutely horribly around the hole. If the embedding is kind of here, one can normalize it, but the hole is a problem, okay? But here we get, okay, so there the theorem is we take as target a ball. Let's fix the ball as a target. And then there is a sequence. Maybe for now, since I have 5 minutes, let's forget this. But if I take the cube of size 1, then I find infinitely many different symplectic embeddings into the open 3 ball. And I think if I tell you this, you can do it as an exercise. Because you use, of course, these tori. Let me first find a second one. So here we have CP2 and this here. YouTube streaming. Okay, this is CP1, so this is the ball, and here I have a fat, beautiful cube. This is something like my first embedding. But then, from the first almost toric vibration, you see, I also have a cube embedding, this one. Unfortunately not, this big cube doesn't fit. But every cube of size 1 plus epsilon, for epsilon small enough, will fit into many of these vibrations. And into the first one, you need less than 1 plus 1 over 5. And for the next one, you must be a bit bigger. But if you are size 1, all of them fit. Now I wish to prove that all these embeddings phi n into the nth almost toric vibrations are different. Okay, so let's do it. So since we have the almost toric vibration comes with a simple ectomorphism to CP2. Here we have this kind of visible embedding. You know, this is really a cube. Or this is really under the standard moment map. You see, away from here and here, this vibration here that I called pi is the same as the usual one. So here with this red square, I mean the usual moment map, like norm squared of the coordinates. And so I have here this embedding when I compose with this identification. First, I put it into the almost toric vibration, and then I view it into CP2. And this is my first new cube embedding. And I wish to show that it is not isotopic to the one everybody would write down. This is when you read it in the ball, the identity embedding, this one. Okay? Okay, let's prove it. The point is, if they were isotopic, then the tori were isotopic, but they are not. Now, but I do it a bit slower. So I wish to prove that for A, such that the second embedding does exist, the two embeddings are indeed different. You assume not. What is this? Okay, if not, this embedding composed with a simple ectomorphism of ambient space would be this embedding. If you want as a set or as a map, maybe I should write as a map. It's a bit easier to prove. So now I restrict this identity to this Clifford torus, right? So here is the Clifford torus. And of course, it's the Clifford torus sits in the C4. And I restrict it to here. The identity does not move it. And what I get is that the simple ectomorphism, the hypothetical simple ectomorphism, maps the Clifford torus to phi of L. But phi of L is the Chekhov torus. But they are not simple ectomorphic, meaning this phi does not exist, contradiction. So they are not. So this is true. I mean, yeah. The fun here is to elaborate the numbers and to see how many there really are. But this is immediate application because cubes are such that this fiber is in the cube. If you would try to do this with ellipsoids or balls, it doesn't work because they would just go through the point somehow. So I need here in the domain a little bit of convexity. I cannot work with such shapes. No, we cannot do that. Okay, so for cubes or for something like a ball that is slightly more convex than a ball, something like this, you can find these infinitely. So it actually means the following, you see. McDuff showed that if you take a ball and then you embed, then they are all isotopic. But if you round it a little bit, they become non-isotopic. So it's very fragile. So this phenomenon was already observed by Usher and Good. Right, sorry to show off. I absolutely wanted to show this picture. If you ask the same questions for embeddings into S2 cross S2 or the affine part, namely also a cube, but this time a target cube, then things become actually much more important, much more interesting, because you don't have only triangles, you also have foregons, and then the triangles are always good as before, but the foregons are sometimes good and sometimes bad and sometimes very bad. The white ones are total bullshit because they don't have a 1, you need a 1. And the green ones, they have a 1, but they do not accommodate the cube. And the red ones and the yellow ones, they are good and they lead to new embeddings. And the complete enumeration, well, already the complete graph is not understood and the coloring of the graph is also not understood. And we gave up. It's already kind of combinatorially so rich that you have, after a few weeks, just give up. Right, Joy? Yeah, I also gave up. Okay, so I give up now. Thank you very much.
So yeah, let's thank the speaker. Yeah, questions, please.
What is your ultimate goal in this, series of problems? That's a big problem people shoot for.
Both, I don't know. So I want to understand kind of the nature of symplectic rigidity and flexibility and the zone of transition. And really to understand what it means. And these, for instance, in the ellipsoid embedding problem, so this staircase, it kind of shows quite rigid, quite flexible, quite rigid, totally flexible. So it's a force, it's kind of fine structure. And so, for instance, these almost toric vibrations they almost halved the proof. And they were then also used to find many more such staircases. So McDuff and Nicky McGill recently wrote a paper where you have so you don't have such a sequence of steps. You have something like a contour-like structure. So these tools, these almost toric vibrations help very much to make progress in the question how subtle and intricate, easily formulatable symplectic embedding problems can be. For instance, McDuff and McGill look at the following problem. They take ellipsoid 1A and they embed. So what we did was CP2 or goal, right? So they blow it up here by weight B. This size here is B. So they have a two-parameter problem. And as a function of B, the type and structure of staircase you get is fantastically complicated, but wonderfully still essentially describable. Thanks to these tools, to all the tools and these new ones and combination of it and observations. Sometimes you need computer codes to guess the right answer, but once you have the right answer, you usually can prove it. So this is kind of business into complexity of fine structure. And then what is fascinating is that in the fine structure from the answer, usually relations to other fields come up, to Diophantine equations or to some lattice count problems. When you work with embedded contact homology, things boil down to discrete isoperimetric inequalities. And so this is a kind of, I cannot say I want to prove the blah, blah conjecture, but what is extremely nice is to move in this field with the new tools and find new bridges to other topics, new phenomena, more richer examples than before. Right.
Thank you.
Maybe another goal would be just understanding exotic Lagrangian tori. I mean,
right.
Because for now there's only some constructions, right, which yield new tori, but there's no classification in none of the spaces. You don't know if you get all of them. For example, for C2, you still don't know if there are two or more. You don't know if the Viana tori are all in CP2 or if there is more. And it looks for now, it looks like somehow just the beginning of understanding them, because you have some different constructions which yield new examples, but sometimes they are related, sometimes not. And
right.
So you think they might be different phases of some large way of combined way of approaching this?
Yeah. If somebody can prove that every monotone Lagrangian tori in CP2 is a fiber of an almost toric vibration, then the Viana tori are all of them, right? If you can come from another side and find a structure theorem then you will be done in this classification.
I see. So it's a conjecture.
It's always each time, first Eliashberg conjectured there is only the Clifford torus, and Gromov, then Chekhanov found the Chekhanov torus. Then they conjectured they are exactly these two. They even wrote the paper. Then Viana found these infinitely many. So I would now conjecture they are all, but it was always wrong, these conjectures. So it's a bit risky. It could be.
So what makes it like so easy when you go from CP2 to like when you replace stuff with to S2 cross S2, but it gets very complicated when you blow up.
Yeah, you have this new parameter. Not for all b values, the answer is, you see, for b equal to 0, the answer is, you mean is this staircase, right? That is not so easy, but less well organized. Then there are other b values where the answer is also like this. But then there are bifurcation values where these staircases disappear, bifurcate, and then come back. And it's not understood for all b values. But something like a fractal structure is understood. It's understood that if you know it for a certain b interval, then you can reflect them around by something like 1 over x around alpha over x for a certain alpha and certain translations. So it's this fractal structure means if a small little interval you would understand, then you understand them all because you can transport around. This is known. But the answer is not everywhere known, because on this interval it's not known. So here really we have one more parameter, right? So b equal to 0 is the old answer, and now there are, for certain values of b, the answer is quite boring. But then you move b again and it comes back, and sometimes it's even more complicated than this staircase, this well-organized one. So there is,
yes, please.
Probably it was not very convincing, but the introduction of the paper by McDuff-McGill is quite well written.
So any other questions? If not, let's thanks the speaker again, and I will stop recording. Thank you.
Yeah.